All right, this is a video on finding the area of some more unique quadrilaterals, I suppose, specifically trapezoids, rhombuses, and kites. We'll go through a few of those formulas and then do a few solved examples. All right, area formula for a trapezoid is as follows. Area is base 1 plus base 2 divided by 2, and all of that times the height. Base 1 and base 2 refer to the two parallel sides of the trapezoid. Doesn't matter which is 1 and which is 2. And then the height is the perpendicular height. In other words, the perpendicular distance between the bases. Okay, so we don't really need to know anything about the left and the right slant sides of this trapezoid to be able to find the area. Okay. The way I like to remember this, though, don't just memorize this formula. I like to think of this as being the average of the two bases. So when we add two things together and divide by 2, we're finding the average of those two numbers. And so think of base 1 here as being sort of a little bit too short, base 2 being a little bit too long. Let's find the average of those bases and essentially turn this shape into a rectangle, okay? And that's kind of how we're doing it. Or that's at least how I memorize it, how I remember it. A rhombus is an equilateral quadrilateral, so it's a quadrilateral with 4 congruent sides. To find the area of a rhombus, you could always just use the parallelogram formula, base times height, but there's another formula that works as well, and we can think of the two diagonals. We can call that diagonal 1 maybe, and then this other one diagonal 2, although 1 versus 2 doesn't matter. The area is just going to be 1/2 times the product of those two diagonals. And you can actually think of that as think of these two diagonals as dividing the rhombus into two triangles. So we have this triangle and then separately this other purple triangle. And that's where the 1/2 really comes from. Okay, so 1/2 times the product of the two diagonals. A kite is down here in the lower right. And a kite has the same formula as the rhombus, although the diagonals may be different lengths. We can still have, diagonal 1 be that diagonal, and diagonal 2 be the other diagonal. And once again, 1 versus 2, which was diagonal 1, which is diagonal 2, that doesn't really matter. But the area, once again, is 1/2 times d1 times d2. And you can kind of see that the rhombus sort of looks like a kite, right? It looks like a kite that happens to have 4 congruent sides. So that it makes sense that it would have a similar area formula. Let's go apply these formulas and get some areas. So we're going to first do a little bit of a real-world problem. Let's estimate the area of Nevada. Okay, Nevada actually is, we don't always think of it like this, but it is roughly a trapezoid with these being the two bases. Okay, so we are going to find its area by averaging the two bases. So 205 plus 511, and then divide that by 2. And whatever the average of the two bases is, then gets multiplied by the height, which is 309. Okay, just keep in mind the height doesn't have to be a vertical up and down height. In this case, it's a horizontal distance or an east-west distance, right? And that's fine. So let's average the two bases. And that'll give us the number smack dab in the middle of those two values, and then we'll multiply it by the height of 309. So I get an area of 110,622 miles squared. Okay, and I challenge you to go actually look up the actual area of Nevada and see how we did. I bet we got pretty close. All right, next one is you will encounter some problems where we need to use trigonometry. In this case, you can see we don't know the height of this trapezoid. So we need to find the height, and we can do that by working in a little right triangle. Okay, I hope you can see that this distance is an extra 2 meters if we consider this distance to be 5. Okay, so we have a little right triangle. We can use trigonometry to find that. This is our opposite side, and this is our adjacent side, and so we're going to use our tangent function. And we can say that the tangent of 60 degrees is our opposite side, which is our height, in this case, divided by 2. We can multiply both sides by 2. And that gives us our value of h. That gives us our height, okay? And that's going to be roughly 3.5 meters. But I'm going to keep this as an exact value right now and do all the arithmetic at the very end, okay? Let's find the area of the trapezoid. We have to find the average of the two bases. And hopefully you can see that's going to be 6 times the height. Okay, so this equals 6 times 2 times the tangent of 60, which is 12 times the tangent of 60, which would be a fine exact answer. But let's go to our calculator and get a decimal approximation. And this is approximately 20.78, and that would be meters squared, square meters. Does this kind of make sense? Does it seem like it makes sense? It makes sense to be a realistic answer. Our picture isn't necessarily drawn to scale, but if this is if this has a height of roughly 3.5 or so, 6 times about 3.5 is about 20, 21. So yeah, so it makes sense. It makes reasonable sense. Let's find the area of a kite here, and we have a little bit of information that we don't quite know yet, okay? For some of these problems, you don't know, for example, for the 12, does that 12 refer to that entire diagonal, or does it just refer to that distance? I'm going to assume it just refers to that shorter distance. If you're unsure, that would be a fair question to ask a teacher. What length is 12? What length is 4? So I am going to remember that kites have perpendicular diagonals, and we need to find this distance. I'm going to call it x right here. Hopefully you can see the Pythagorean theorem would be a pretty friendly tool to use here. We have a 3-4 triangle, 3-4-5 triangle, so x is going to be 3. I hope you can also remember that kites have symmetry down that major longer diagonal there, and that would give us a 4 over here as well. So let's apply our formula. Area, remember, is 1/2 times the product of the two diagonals. So the area is 1/2. The longer diagonal has a total length of 15, and the shorter diagonal has a total length of 8. And good chance to do a little mental math. Let's associate these two together, group those together first to get a 4. What's 4 times 15? That's going to be 60. And that's going to be 60 square units. It's going to be the area of that kite right there. All right, and lastly, we'll do something similar with the area of this rhombus. Remember, the area of a rhombus is 1/2 times the product of its two diagonals. Okay, and once again, you need to be thinking about what distance does, say, that 2.5 refer to. The 2.5 looks like it's half of that full diagonal to me. So my area is going to be 1/2 times 5 times, we don't know what the other diagonal is yet. But once again, we can use the Pythagorean theorem, so I'll draw that upper right triangle here. And let's see if we have a hypotenuse of 6.5 and a leg of 2.5, we can find x right there. We can say that x squared plus 2.5 squared is 6.5 squared. So x squared plus 6.25 is equal to 42.25. Oh, and this is going to be pretty friendly. X squared, once we subtract 6.25 from both sides, x squared is 36. So x is an exact 6 feet. Okay, so I hope you can tell that this distance, which I'll try to highlight in red right here, that's not really showing up. This distance right here is 6 feet, so the entire diagonal is 12 feet. So I'll throw in a 12 into my formula here. 1/2 times 5 times 12. Again, try to use some mental math. Let's do a 1/2 times 12 first to get a 6. 6 times 5 is 30. So we have a 30 square foot rhombus right there. All right, so remember those formulas, but don't just remember them. Remember where they came from, and that'll help you kind of figure them out if you forget the actual formula. And that's a good place to stop right there.